Take me to the frontier of particle physics today.
There's tremendous progress being made. It's such an exciting time in fundamental physics. Not only particle physics, but we said gravitational astronomy, the exploration of the force of gravity, black holes, quantum information, quantum computing, and all sorts of all that stuff is to me utterly fascinating. I think for the first time, it's probably true to say in particle physics, we don't know if there's anything else just around the corner, which is bad. But it is our duty to find things out about nature.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. And today we are featuring my exclusive one-on-one interview with my friend and colleague from across the pond, Brian Cox. Brian, welcome.
Oh, it's great to be back.
Oh my gosh. Oh, it's been too long.
Yeah. And we don't usually get to do it in person. It's usually over Zoom or something.
Right. Let's get some of your biography out there for stateside people who might not fully know who you are. You cut your teeth as a particle physicist. Is that correct?
Yeah, initially. I mean, actually, my degree is at the University of Manchester, by the way, in the UK. I've never left. So I started there doing my undergraduate degree, postgraduate.
What do they call you there now? You are professor of particle physics at the University of Manchester.
Yeah.
And Royal Society, as in the Royal Society of London?
Yeah.
Royal Society professor of public engagement in science.
Yeah.
So we're kindred souls across the Atlantic.
Yeah.
So, okay. So you never left. Is that because they wanted you so badly or that no one else wanted you?
Yeah, probably the latter. But I started, it was actually physics with astrophysics, my degree. So I did a degree in physics with astrophysics. Then PhD in particle physics, although the first year I was working on supernova neutrinos. So I was crossing over astroparticle physics, as we would call it. Then I got into particle physics, went to the DAISY laboratory in Hamburg and worked on electron-proton collisions, so-called diffractive scattering.
I've seen DAISY online. I've seen DAISY simulations of things. They simulate like colliding black holes and things. Fascinating. DAISY.
DESY, the Deutsche Elektronensynchrotron.
Yeah, but they have a public-facing platform.
See, I didn't know that.
Yes,
I didn't know.
Yeah.
Because the accelerator is no longer operational there.
Okay.
So, but it's a huge lab in Hamburg.
Mm-hmm.
So I did my PhD there. That's in particle physics. Then moved to Fermilab in Chicago for a while. And then to CERN when we were building a Large Hadron Collider. And then, but I've always...
CERN, Switzerland, yes.
In Geneva.
And remind me, that's the European Center for Nuclear
Research. Yeah.
Acronym, French acronymed.
Yeah, because it was founded in the 1950s. And at the time, so it was what part of the reconstruction of Europe really after the war. So it was that lab was founded, I think it was 1954, 1953.
Mm-hmm.
And so it was nuclear physics at the time. There wasn't really such a thing as particle physics, I suppose, at the time. Mm-hmm. And now it's by far the world's largest accelerator, particle physics lab.
Yeah, I mean, the center of mass of that whole world left the United States when we stopped funding our supercollider.
The SSC in Texas, yeah. The SSC, superconducting
super collider.
Yeah.
Yeah, I would have called it a super duper collider that might have kept its funding at that point. But so Europe still leads the world in nuclear particle research.
It's a very international lab. I mean, it is the world's collider.
Mm-hmm.
So although it's based in Switzerland and France, I would say it's a world lab.
Okay, that's very diplomatic of you.
Well, it certainly is. I mean, the US have a tremendous presence there, for example.
While you're saying all this to me, you're not describing this branch of your life as a musician. So just briefly remind me of that.
Yeah, so when I was 18, traditionally you would go to university there, start a physics degree. But I didn't because I was in a band, a rock band, that I joined just before
I'm sure your parents loved that fact.
They did actually. They loved it.
I could go to college and major in physics or continue with my band.
Well, but do you have that thing like a gap year, we call it, where you say, well, I'm going to take a year off the studies before I go to college or university? And so I'd said that. I'd said, I'm going to be in this band and I'm just going to do it for a year and then I'll go and do physics. But then we got a record deal, a big record deal with A&M Records. This is in 1986, 1987. It's a long time ago. Got a big record deal. And so I came to Los Angeles and recorded an album with actually produced by Larry Klein, who was married to Joni Mitchell at the time. And so we recorded some of it in Joni Mitchell's studio in Los Angeles. So, and then we toured with, my first professional gig with that band was with Jimmy Page, the Foot in Jimmy Page. And
did you open for Jimmy Page?
Yeah, we opened for Jimmy Page and Gary Moore, who'd also been in the band, Thin Lizzy, and then Europe, the Final Countdown. So you know this song, The Final Countdown, and Carrie was a big hit here in the US. So we opened for them. Made a couple of albums. So I did that basically for 5 years.
And it charted?
Actually, no. We did big shows. It was a rock and roll band. And then I left that band, went straight back to Manchester and went to start a physics degree.
As one would do, yes.
But then in that little gap, I joined another band who then had some hit records. So a band called D-Ream. This is in the early 90s now. And they didn't have a record deal when I joined them, and they got a record deal as well. So when I was at university, I was in this band. We had a #1 hit in the UK and Australia with a song which violates the second law of thermodynamics, which you'll love, called Things Can Only Get Better, which is clearly incorrect. Certainly,
things can only get worse. Globally in the universe. Yes.
Exactly. So I had a two.
Wait, and that song, what helped it, if I remember correctly, some political candidate adopted it as their theme song.
Tony Blair. It was Tony Blair. Yeah, it was Tony Blair in 1997.
It became a big election. Associated with his election.
Yeah, and came back actually into fashion because we just had a change of administration in the UK, and that song came up again, and it came up and it got quite popular again. So I did Glastonbury this year with the band.
Wait, that's that huge place.
Yeah, the big festival. Yeah,
that's any huge scene of musicians in the UK is at that location.
Well, it's probably the biggest festival in the world, I would imagine. I would guess, but it's a huge festival.
So you and Brian May.
We are the two. He did it the other way around though. He got extremely he got extremely famous and then finished his PhD
in astrophysics. Yeah. Okay. Brian May, lead guitarist of Queen. Yes. Yeah. So let's pick up some of the physics. We are both here right now in Las Vegas at a World Skeptics Conference. Yeah. We're both skeptics. I mean, any scientist is a skeptic, but the problem is when the world does weird things, who's going to put them in check? Somebody's got to show up at the scene and say, no, that's not how that works. Or no, the laws of physics prevent that. Or you've had to do this in the UK, right? There's certain resonances between the United States and the UK about how people misthink things. So what was your baptism into this world?
Well, actually, I mean, I was only interested in doing research for a long time. So as a postdoc and in that part of my career, I didn't want to know about anything else other than doing research. And that's all I did. But it was, I can't remember when it was now, but there was one of those regular funding crises, as you'll know from here in the US, when government support, in particular for research, dipped. And so I got involved in trying to fight that. And we realized, I mean, it's kind of obvious, I suppose, but we realized that one of the reasons, talking to government, that they had cut the research budget was that they didn't think anyone cared. So they thought it was a simple thing to
democracy.
Do. You could just, and so we all, as a community, we were we learned again. We've learned it over the years, but we learned again that popular support for what we do is important. And where does the support come from? It comes from understanding. And there are many reasons, by the way, why talking to people who are not in science about what we are doing as scientists is important. One of them, of course, is just purely democratizing knowledge. We taxpayers fund, at least in part, what we do, and therefore they have a right to know. So there's that level. But on the other level, which I think you're suggesting as well, what science does, I think it's not about knowing the facts. Like it's not about knowing the universe is 13.8 billion years old, for example, or it's 13.8 billion years since the Big Bang. We could talk about that later, actually. Does that mean it had a finite origin in time in the past? Anyway, But it's not
We'll put a pin in that. We'll get back to that, okay?
It's not about knowing facts so much as understanding something about the process by which we acquire reliable knowledge about the world. And science is the process by which we acquire reliable knowledge. And so I think that
it may be unique
realized
in that. That.
Well, in the sense that nature is there, whether the job of the scientist is to find out how it works. And it, of course, as Richard Feynman and many others have famously said, it doesn't care who you are or what your opinion is or how popular you are or how many votes you got or anything, how much money you've got. It just doesn't care. So in that sense, I think it is a unique pursuit because the standard by which your opinion is judged is external to us. It's nothing to do with humanity.
Nature is the ultimate judge, jury, and executioner.
Yeah. So I think I became involved initially just on that very narrow idea that we wanted to make sure that people understood what we did and what the value of it is. And then that branched, that became bigger and bigger in my career and branched out into television and live shows and all sorts of things. But it came from that. I wasn't interested in communicating science. I was just interested in doing it for a very long time.
So you had a certain duty and responsibility to the world.
Well, I think we all do. I mean, I've realized since that I think actually Feynman again said it's a very brilliant essay that anyone can download from 1955, I think it is, called The Value of Science. It's just 4 pages and it's on Caltech's archive, I think. And in there, he says that it is our duty as scientists, our duty, knowing the great value of, he defines science as a satisfactory philosophy of ignorance, which is a beautiful, just merely satisfactory, it's a philosophy of ignorance. You start out from not knowing. And he said the great value of the satisfactory philosophy of ignorance, the great value of freedom of thought, to proclaim that freedom and to try to protect it for all coming generations, he essentially says at the end. So, but I like the framing. It is our duty as scientists to do that, as well as do our job, which is to find things out about nature,
about the natural world. And in this conference, I am to bestow upon you the Richard Dawkins Award for Science and Reason.
Bestow,
yes. The Richard Dawkins Award is something I won last year, and I was called back in to bestow it upon you.
Passing a torch.
It's
a great honor.
It will be a delight for me. It takes place tonight.
Yeah.
I look forward to that. And just the idea that science and reason is something, maybe it's sad that it's something that needs to be rewarded because if it's one of these awards that if the world functioned just right, you wouldn't need it.
And also, although I said, as Feynman has said, it's in a sense our duty as scientists. It is also true that not all scientists want to do that or feel comfortable with it. As I said, I didn't want to do it initially. Now I very much enjoy it and think it's very important.
Launches, Elon Musk is turning visionary ideas into real progress. However, since his cabinet appointment in Trump's administration, many are wondering about Musk's conflicts of interest, his influence on policies, and more. So tracking developments through reliable sources these next 4 years is absolutely essential, something our long-term partners at Ground News simplify. They're an app and website founded by a former NASA engineer who brought the same level of precision she needed up in space to how we consume information here on Earth. Access every perspective shaping a story with data on how credible their reporting actually is. Or burst your media bubble and find important angles impacting space and beyond you might have otherwise missed. With science increasingly becoming a political talking point these days, access to a platform designed to bring clarity to even the most polarizing topics has never been more important. So head to ground.news/startalk or scan the QR code to subscribe to Ground News today. We're giving our viewers...
Take me to the frontier of particle physics today. What's going on at CERN now that the Higgs boson is discovered and the Nobel Prizes were granted? What are they doing now?
Well,
did they just close shop and go home?
No. I mean, what particle physics is because we're talking about quantum mechanics, basically, it's statistical in the sense that you collide. What we do there,
circumference,
yes, that's about 16 miles or something like that, and the protons go around that ring 11,000 times a second. So that's how fast they go.
That's fast.
So that's 99.999999% the speed of light.
Okay, so you've granted them energy so that when you collide them, you break them apart. You're basically deconstructing nature to see what residue comes out of it. When I think of doing that for anything else, it's going to break, right? I don't take chairs and slam them together and still have chairs. I have a pile of kindling, okay? So who ever thought it was a good idea to smash nature into itself?
Well, I suppose Ernest Rutherford initially. So we go back to Manchester, the turn of the 20th century, and Rutherford was using radioactive decay to essentially produce the particles. I mean, it's just the decay of atomic nuclei that naturally happens to produce high energy particles, which he then fired into gold foil and bounced them off the foil. In doing that, he discovered the atomic nucleus. So one way to think about particle physics is that when you collide things together, what are you doing? You're really building a microscope. One way to think of it is that the higher the energy of the collision, the faster these things are traveling, the smaller the objects you can see. So we were talking about seeing for the first time in those experiments the atomic nucleus. You move forward to ultimately through the 50s and 60s, when we have higher and higher energy collisions, you start seeing that the nucleus is made of protons and neutrons. And then you start seeing it in the 50s and 60s that the protons and neutrons are made of smaller things called quarks. And so we discover those. We've not discovered anything smaller than that, by the way.
Is it because you don't have enough energy to bust up a quark?
Yes. Or to resolve what's inside it, let's say, to build a microscope.
Because right now, the inventory of fundamental particles includes quarks.
Yeah.
So somebody saying that's fundamental, which sounds a little like the Greeks saying atoms are fundamental.
Oh, no, well, they won't be fundamental. You're absolutely right. But they look point-like from the point of view, from the energies that we can generate today. But that's one side of particle physics. So we've been exploring the structure of matter, which is historically, it goes back to Rutherford, I suppose.
And again, you have confidence that when you break matter apart, you didn't break the matter. You're just deconstructing it.
Yeah, it really, I think the way to think about it, you think about what a collision is. So let's say you collide, as we did in my PhD, electrons and protons together. So you get an electron beam and a proton beam and you smash them into each other. What's actually happening? What's actually happening is one way that the collision can happen is that the electron can emit a photon, which is a particle of light. And the particle of light goes and it hits the proton. Now, the wavelength of that light, which telling you how small a thing you can see, is proportional to the energy of the thing. That's how hard we're smashing the things together. So the faster you smash them together, the faster you smash together, the higher the energy, the smaller the wavelength. So the smaller the things that you can see. So that's a way of thinking about particle collisions. So it really is a microscope in that sense. Okay. That analogy works.
I'm just thinking, if I were a proton, I wouldn't want to be busted apart into quarks. That would not be a nice day for me.
In some ways, I suppose it's kind of like having an X-ray, I suppose, isn't it? You're right, though. You hit them hard enough and they fall to bits, but that would be the same for you. But we would try not to hit you that hard.
The bits that I fell into, no one's considered them fundamental bits of Neo. Right.
But the other way to think about particle physics, which is, I think, so you say the Higgs particle you mentioned. So that's not in the proton. You're not smashing the things together and finding a Higgs particle buried in there somewhere. The other side is really, so you think about Einstein's famous equation, E equals mc squared. So energy and mass are interchangeable, let's put it like that. So it also says that if we have loads of energy in these collisions, then we can make new particles that are extremely massive, much more massive.
That would come spontaneously out of the available energy that would otherwise be doing nothing.
Yeah, so we have, when you collide protons together at these energies, you have plenty of energy there to make a Higgs particle, for example, or a top quark, which is a very heavy particle as well, far more massive than the protons. So that's, I suppose, the way to think about trying to manufacture Higgs particles. So you can observe them. You need enough energy to make them.
So you're not just busting them apart. You're creating an opportunity to view more massive particles than would otherwise be available to you.
Yeah. And the other thing to say, so to get a complete picture, is these very massive things like Higgs particles, they have a very short lifetime. So you make them and they decay away into lighter particles very, very fast. So you don't see the Higgs particle. What you see are the debris from the decay of the Higgs particle. And the challenge of particle physics is to detect all those bits that came off, basically. And by the way, you also have the bits of the protons that all got smashed up as well. So it's a big mess. And we have more than...
I've seen these
these. It's very hard because you don't only have one proton collision per... We send the particles around in little bunches, basically. So you can get 10, 20, 30 collisions at the same time. Only one of them on a very good day will be an interesting one. And then, so you've got to sift through all this, which is the difficulty or the professional challenge, let's say, of particle physics.
With that reasoning, there's always some next energy level that you haven't visited.
Yes.
Where more and interesting physics can reveal itself.
And this is where it gets challenging at the moment, because so the so-called standard model Higgs particle, and I should just say for a minute that thing, the existence of this thing was predicted in the 1960s by Peter Higgs and others. And it was a suggestion, a theory, a guess, let's say at the time, mathematically motivated, almost purely, by the way, mathematically motivated, of how things get mass in the universe at the most fundamental level. So how the quarks and these very heavy things called the W and Z bosons, that how those things got mass. And so it was a mathematical construct. It predicted that there should be, in the simplest case, this thing, the Higgs boson, but there could be more complicated versions. And so we knew that if we collided protons together at the energies that we generate at the Large Hadron Collider, then we would either discover the Higgs boson and prove this theory to be correct, or we knew that if it wasn't there, we would see something else. So we had a very clear idea from experiment and theory that we were going to discover something with that machine. And you don't know what it is. It turned out it was the simplest thing. Mm-hmm. It was this thing that Peter Higgs had dreamt of all those years ago, which is astonishing, by the way, 50 years after the prediction. And there's a great essay that you might know by Eugene Wigner called The Unreasonable Effectiveness of Mathematics in Physical Sciences.
Yeah.
I think that's one of the best examples. It's an astonishing achievement that we got it right. And so we discover the Higgs boson.
To put precision on that Wigner's the point in that paper, it's not that math in a vacuum, no pun intended, makes discoveries. It's the mathematical representation of a physical idea.
Yeah.
And then you pursue the math and it applies to the universe, but only if the physical idea has captured reality in some fundamental way.
Although it was, I think, it was a very mathematical framework which became the standard model of particle physics based on ideas of symmetries and all sorts of beautiful ideas, which really did have mathematical foundations. So there's an aesthetic sense, I think, built into that model.
And that would be the pure mathematical. See, my people in astrophysics, we have enough embarrassing historical examples of chasing elegance and beauty.
Kepler,
I'm saying, look at Kepler.
But I think the genius of Kepler was that he had these platonic solids and these ideas.
Right, he's got the pyramid and the cube and the this and
but then he rejected it based on data.
Yes, but his first thought was the universe is beautiful and divine and perfect, and these solids are perfect. Planets are in the universe, so it must be a connection. Yeah, he spent 10 years looking at it.
Yeah, but then
he rejected it.
And then the laws of planetary motion, which are indicative of a very beautiful thing, which is Newton's law of gravitation, an inverse square law.
Yeah.
And so there's a beauty underlying it.
But only after he had to scrap this other beauty that he had presumed it would be. That's why we step lightly when someone says, I have this beautiful idea. Yeah, okay, let's hear it.
But it is true that I think it's one of the great mysteries that there is historically, Einstein's theory of general relativity is another example where a quest for simplicity and beauty and elegance, which are judgments, right, the human judgments, has led to very, very precise models of the way that nature works.
Given that CERN, which has the Large Hadron Collider, LHC, discovered the Higgs boson, if you're going to discover more particles, presumably you have to keep sort of upgrading the system as the LHC was compared to what was there before, so that you can with ever greater force, bust into the particles and see what's lurking.
So we can't increase the energy of the LHC very easily. Or even easily, or even we can't really.
At all.
So that would be a major change to the machine. But what we can do and are doing is so-called high luminosity upgrades, which means you collide more protons together. And the thing about
so then you win on the statistics of the event.
because particle physics is a quantum mechanics, and so things happen statistically. So it's, one in, I don't know the numbers off the top of my head, 1 in 10 billion collisions you'll produce something interesting. A Higgs, it's less than that. But so when giving yourself more collisions gives you more chance to discover new particles, and it gives you more particles like Higgs bosons to explore.
If you get a Higgs particle after however many collisions, and that's kind of rare, if you have more collisions, you'll get more Higgs to improve your statistics on what the hell the Higgs is.
Yeah, because we want to know.
But then there could be a reaction that's even rarer to manifest than the Higgs.
Yes.
And if your sample wasn't large enough, you would just never go there.
Yes, you wouldn't see it. If you just made one thing, one particle, whatever it is, the Higgs prime, whatever. If you made one of those, then prime. You wouldn't see it if you made one of them.
Sounds
right?
like
you need to make hundreds.
Superhero nemesis. I'm Higgs prime. I've come to destroy.
By the way, and we do look for those things. The Z prime, the Z boson, we look for the Z primes because they can be signatures of extra dimensions in the universe, by the way. So we look for this stuff. But the point is that if something is very, very rare, then you won't really see it. If you just make one or two of them, you need to make hundreds or thousands or whatever it is to see them.
Yeah, it's like how many people have to live in a city before you stumble on someone who's 7 feet tall?
Yeah,
that's
so statistics.
Statistically, you need possibly millions.
Yeah. So the upgrades are the upgrades that we can do, and you have to upgrade the detectors, the cameras that we use, as well as the machine.
Okay, so you kept the same hole in the ground.
Yeah, because we don't want to dig another one of those or change all the magnets around, which are very expensive.
Does that hole go through more than one country, or is it all contained in Switzerland?
It's France and Switzerland.
Wow, okay.
Yeah, most of it's in France, actually.
Oh, didn't know that.
Only a little bit of it's in Switzerland.
Okay. Good.
So that's one thing. And the other thing is, this Higgs that we've discovered, the question still remains, is it the simplest one, the standard model Higgs, it's called? Or is it something more complicated? How does it behave? So the analogy in planetary science would be, we discovered a moon. And so you go, great. Then you would like to know about the moon. You don't want to just say, we've discovered this moon, it's a dot. That's fine. As you said, they're interesting.
You want to characterize it in whatever way you can.
For that, you need a lot of them to observe. Mm-hmm. So it's exciting, and it's challenging because I think for the first time, it's probably true to say in particle physics, we don't know if there's anything else just around the corner, which is bad, but it's also good. I suppose it's just science. I mean, ultimately, it's neither bad nor good. It's the way nature is.
That's what triggers whatever next round of physics is complete.
Yeah.
You get those people that show up and say there's nothing left in physics to discover.
Well, they
show up every few decades.
So utterly wrong that they're not even worth considering. I mean, there's tremendous progress being made. It's such an exciting time in fundamental physics at the moment. That not particle physics, not only particle physics, but we said gravitational astronomy, the exploration of the force of gravity, black holes, quantum information, which is related to quantum computing and all sorts of, all that stuff is to me utterly fascinating. There's some really interesting stuff. I read some stuff the other day, which I don't fully understand, actually, some of the progress in string theory. It's interesting because, just as an aside, it's linking, it seems to me, it's linking one of the great mysteries, which is the so-called cosmological constant. So the fact that we observed that the universe is accelerating in its expansion.
And Nobel Prize has been given for the observation,
Brian
not for the
Schmidt.
understanding. Yes.
Yeah. There's a friend of mine who, by the way, didn't believe he didn't believe it when he saw it, because it wasn't in the air, this idea. He was looking at light from supernova.
Right.
Supernova.
Like I'm on a paper with Brian Schmidt.
Yeah.
I'm like a very minor author. You got to scroll down, and then like my name is
in the supernova date. Yeah.
But it was analysis of high redshift supernovae.
Yeah.
And I totally enjoyed that work. But he obviously went on and made an entire sort of branch of his career on it.
So there's this remarkable idea which comes from that, which is in Einstein's theory, this idea that you can have a kind of energy in the universe, let's say, or a thing, whatever it is, because we don't know what it is, but something that makes the universe, the rate that space stretches, increase, which is so that's there and it's observed. It's one of the great mysteries because I think it's the smallest number in all of physics by, what is it? It's something like a 10 to the power minus 122 or something in appropriate units, right? Which is an absolutely ridiculously, so it's a tiny, 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 tiny thing that's causing this rate of expansion. But it's not zero. And so the question becomes, why is it tiny?
Why is it tiny and not zero?
Yeah.
Right.
And so, because if it were even slightly bigger, we wouldn't be here. So the universe would have been blown apart. So it seems very unusual. But I saw the other day, actually, that there's some research that's linking that in the framework of a string theory, or M theory, to dark matter. So there's a kind of an idea that if you fix that, you get a prediction out that there should be dark matter, but it turns out it's to do with extra dimensions and gravitons in extra dimensions and things. So it's quite interesting. So I think there are some very interesting areas of string theory where progress is being made quite remarkably.
Do string theorists need a fuller or better inventory of particles? So, for example, are we still looking for a graviton? Are we still looking for, you shake a stick and there's a physicist proposing a hypothetical particle to explain dark matter, to explain whatever.
Wouldn't it be cool if the dark matter were related to gravitons, which is this is not my field. I only heard of it the other day, but it sounded interesting. But it just shows you that so to go back to LHC, we have the Higgs particle, as you said. We had expected, I would say most particle physicists expected there would be other particles discovered. There's a particular
in
theory.
that same experiment.
Yeah, at LHC. So there's a particular theory which motivated by string theory a long time ago called supersymmetry, which is a property of the universe.
It's been around for many decades.
Yeah, and it came initially either from string theory or from some other physics and got incorporated in. I can't remember historically which way it came, but it essentially predicts that there are double the number of particles that we see, fundamental particles at this energy. So we, and they would have been great candidates for dark matter, by the way, which is an astrophysical discovery. So we should say, I suppose, the one sentence description of dark matter is that we see the universe. There's far much more matter in the universe than we can see.
See, I would put it differently.
Yeah.
I would say it's not dark matter, it's dark gravity.
Well,
you say matter, we don't know what it is.
Well, it's true. So you see it through its gravitational interaction.
So it's dark gravity.
Yeah.
We don't see, otherwise you get newspaper headlines say, we must abandon our ideas of dark matter. Well, if it's not matter, it's still there. Okay, it's misnamed.
Yes, I see what you mean. I mean, I that's a cool newspaper, by the way, that would have a headline like that.
That it goes there at all.
It's usually about a football player, and so I'm on board with that newspaper.
But, I'm just saying, if we don't know what it is, we had no business calling it matter at all.
But, so the thing to say though
is
that
dark gravity.
The best,
which sounds cool.
So you build models, and it is true that the best model that fits all the data, which is not just the way that that galaxies rotate and collide and the way that gravities, galaxies kind of lens light and all those things, but also the cosmic microwave background radiation, which is the oldest light in the universe, and how that worked and how the ripples, the sound waves went through the early universe and all that. You put it all together and it fits if you have a light-ish particle that does not interact with light, but interacts weakly.
So this would be another category of particle in the particle soup.
Yeah. So
that has gravity, but doesn't interact electromagnetically, or only very weakly.
You can't see it.
And so it's all right.
Yeah. So that's a model, though. You're right. So that's a model, which is kind of, I would say, the baseline model.
It's the assumption. People assume that. And I don't have a problem with it. But if anything happens to that model, it gets shown it can't be true. People say, oh, then there is no dark matter. No, there's still dark. It is a measurement in the universe.
Yeah, I understand.
We've just misnamed it.
Yeah, I agree. The measurement is just galaxies spin round too fast.
But too fast. There it is.
Or the way they collide, and so on. There's quite a lot of independent measurements of this thing.
So tell me about graviton. I mean, is that a real particle?
I think most physicists would say that quantum mechanics is the base theory. I think the reason I'm careful is because there are some people who would say general relativity is a thing, space-time is a real thing and all that. But I think that generally most people would say quantum mechanics is underlying it. And that if you have an interaction...
In other words, quantum physics is foundational to the universe in ways that even general relativity would not be.
Yeah, so we could talk about this later, but the idea that space and time, or space-time, emerge from a quantum theory is very fashionable at the moment, partly because of the study of black holes. So we could talk about that. So given that, then I should say, just for people who are watching and listening, that so how would we picture the electromagnetic force in particle physics? So we know that if you put like charges together, they repel and so on. So what's happening there? Or if you bring magnets together, right, they repel each other. Everybody knows the North Pole together and they repel. So what's happening? In particle physics terms, you picture that as the exchange of a photon. It's a particle of light, goes from one particle to the other, and essentially carries the force. So that's what our particle physicist would picture that force. All forces.
Have we successfully applied that to gravity?
No. So that's the point. But
give me a more resonant no.
The very strong. I suppose I'm trying to find the right word for it. I think that's why I said conviction. It's almost, I don't know of any physicist who would disagree with this
statement. Because if you can't fold it into the quantum world, you don't really have a right to start looking for a graviton. Because you're going to say the graviton is the mediating particle.
Yeah, so it's the photon.
In the way the photon is the mediating particle.
So, and that's, I don't think you'd find anyone who would disagree with that statement.
Okay.
Although, I don't think you would. Although it is true to say that because gravity is so weak, so this is the other thing to say, it is tremendously weak compared to the other three forces of nature, of which electromagnetism is one.
Here's what I tell people, you've surely done this in class. They say, well, how weak is gravity? Well, I can pick something up off the floor against the wishes of Earth.
Exactly, yeah.
Yeah. The whole Earth is pulling on this ball, and I can just pick it up off and kick it into the goal.
And you're using electromagnetism. That's what's happening. So your muscles and all that thing. So this is all electromagnetic force, which completely destroys, as you said, the gravitational force.
Right.
But gravity is only additive. So it only adds up in the universe. So it is the dominant force on cosmic distance scales. That's the point about gravity.
Here's a calculation I haven't verified, but it sounded legit. Very verifiable. Yeah. I was too lazy. That if you take like the space shuttle in its glory days, and you remove the electrons from 1 cubic centimeter in the nose of the main tank, and take all those electrons and put it at the base of the launch pad, would not be able to launch. The attraction between the electrons at the base of the launch pad and the net positive charge at the top is enough to prevent it from launching.
Yeah. That's a cool idea.
Yeah, cool.
I could see that would be.
Yeah. Actually, it would burrow a hole. So
it'd pull it. Yeah.
It's not a realistic experiment, but to get some sense of the forces involved.
Yeah, that's a really nice way.
Okay, so gravity's weak. That somehow bails you out of this problem?
Well, it just means that we don't have experimental access to them.
Okay.
Because it's so weak. So,
whereas we do have experimental access to photons.
yeah, unless you could potentially have access if there were extra dimensions in the universe that are configured in the right way.
Physicists are always throwing in extra dimensions. Whenever you need it, you know.
It is interesting, though, that string theory works in 10 dimensions and only 10 dimensions mathematically. So that's an interesting observation, right? So
I mean, I don't have the background to be an authentic string theory skeptic, but I know physicists who are, and so
I think there are. I mean, it depends. I think it depends what you mean by string theory. I mean, if you go back, a few decades, you talk to Brian Greene, for example, and when he started working in this area, he's
a friend of StarTalk. He's been on us several times. He
would have, and his great book, The Elegant Universe, is a beautiful description of string theory. And so I think the idea initially with the hope was that you'd have a theory and you could write it down. It's a theory of everything, and it would predict the universe as we see it.
And then you go home, and you're done.
And I think that's gone as an idea. But the basic idea of these, I mean, why is it called string theory? It's because particles are not point-like. These strings are like little loops, but that idea, I think, is still at the foundation of most modern theoretical physics in this area. But it's got much more complicated, and it's been much harder. I think the initial idea that you could just predict everything from one number maybe has gone away.
One simple equation on one line.
But there is tremendous progress being made in string theory. So it's not gone away. It's just become more complicated, I would say.
Well, thanks for catching me up on this. At this conference, you're giving a talk on black holes.
Yeah.
And there was some recent announcement, the biggest jet from a black hole ever discovered, ever. When I was asked about it by the press, I simply said, there's always a biggest jet in the universe. And so now this one is that.
It's the A380.
Okay.
So Airbus A380. It's a fantastic aircraft.
Did I undersell the significance of this huge jet? So what if it's the biggest one, unless there's some interesting physics that's coming out of it?
The area that I share a PhD student who's working in the area is more theoretical. It's about quantum information, the way that information behaves inside and outside a black hole, what happens to things that fall in. But in terms of the astrophysical work, if you go back, not long ago, we didn't really have any observation of how things behave in the vicinity of black holes. And so I would put it in that box. We've got several observations now. We've got the radio telescope observations from the Event Horizon collaboration that are showing us how the magnetic fields work, for example, around the black hole in the Milky Way. We've got these jets, which are giving you access to the magnetic structure, presumably, in the way that they spin.
Thank you for putting it in that context. Now I can understand. It broadens the astrophysical data set on which we can sharpen our hypotheses for what's going on.
Yeah, because they're hard things to observe.
Yeah.
And of course, you can't observe the interior because it's inside this thing called the Event Horizon. But what you can do, and we are doing, is observe the way that material behaves in the vicinity of them. Or the other remarkable thing we've been able to do in the last few years is watch them collide and see how the ripples in the fabric of the universe come out, and we can detect those ripples. So all these things are allowing us to probe these objects and it's worth remembering that they were present. They were described, non-spinning ones were described fully by the work that Carl Schwarzschild did in 1916. So months after Einstein had published the theory of general relativity. He didn't know it at the time, but the mathematical description he found, which describes how space and time are distorted in the presence of a star, a non-spinning star, which is kind of important, those fully describe a black hole that isn't spinning.
If I remember correctly, he would die in the First World War. I don't think he made it out of the war.
No, he died in 1916, so shortly after... not in action. He died
was not in action. Okay.
I think he died from diseases that he was on the Russian front.
Okay.
So it was
It could be war related, but not.
Yeah, it was.
From an injury.
I think it was. Yeah, you would argue war related.
So we've got more than a century of mathematical foundation for this. Yeah.
And then you go forward to 60s.
With no data. No, and
then so it takes another 50 years, by the way, for someone to work out what it looks like for a spinning one, which is Roy Kerr. famous Kerr solution. But those two solutions are there. They're in Einstein's theory in a sense, and they describe the black hole. But observing them is something that we haven't been able to do till recently. So
and multi-wavelengths as well.
So now we have radio observations, the gravitational wave observations.
So I'll be a little kinder to that.
Well, because it's the way. The thing is, as you said right at the start, science is about having ideas, building theories, and so on. But it's really fundamentally about testing those theories.
Yeah.
And so we can talk about these theoretical objects, black holes, but really, and they are rich theoretically, but ultimately you've got to make observations. And that's where these jets and seeing how material behaves, it gives you access to the magnetic fields and how the thing's spinning and what it's doing. That's important.
Hey, StarTalk fans, I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. Let's talk about your work with the public. You said earlier you share this commitment that Feynman declared, duty to bring science to the public. You not only talk the talk, you walk the walk, and you have spillage everywhere. You get given tours, public tours in Australia, across Europe, and if I remember correctly, you're coming back to the United States next spring to give a tour across the country.
Yeah. It's a tour that's been going on for quite a long time. It wasn't meant to really, but we've ended up playing to over 400,000 people across the world with this tour.
Wait. So, you're not a musician. You say playing. Get your vocabulary straight.
I'm rock and roll, basically. I always have been that. So, and when we
playing
tour,
to 400,000.
We have 5 trucks and 2 tour buses. It's brilliant. So I'm reliving my life as a.
So did I see a version of that when you came to the city?
Yeah, it was very early on. Just after. Yeah,
you have these screens that interlock.
Yeah,
and then the whole stage is.
Yeah. And that was a very early iteration of this. And so it's changed a lot. Before I laid it to rest, this tour, and develop another one, I wanted to bring it back here in the form that it is now, which is so radically different from what it was.
And it's you celebrating the universe with and for the public. It
also morphed into, there's a version that I do with the symphony orchestra, which is great fun. So I did it at Sydney Opera House, actually, initially last year. And it's a big orchestra because it's 90-piece symphony orchestra because of the music that I chose. And so the reason, by the way, that as a slight digression, it's part of this tour, that classical music is a big part of the tour. So it starts with Sibelius' Fifth Symphony, the third movement. And that was because a conductor friend of mine called Daniel Harding, I said to him, what should Stanley Kubrick have used in 2001? As a joke. Like, what should he have used? He immediately said Sibelius' Fifth Symphony. And it was written in 1915, same year that General Relativity was published. But it's the basis of almost every science fiction theme you've ever heard. Right? You'll hear everything in it. It's beautiful. Okay. So the idea, which I've always strongly believed, but it came to my mind as I was doing this tour, is that what if we're talking about deeper philosophical questions, which are raised by cosmology, I say right at the start, what does it mean to live a finite, fragile life in an infinite, eternal universe? Right? Is it because it? And I say, of course, I don't know the answer to that.
Does that uplift people or depress them?
Well, but it's that, as you know, the moment you contemplate the scale of the universe, and I should say, we don't know whether it's infinite, we don't know whether it's eternal, right? But it could well be infinite and eternal for all purposes. It kind of is, right? On a human scale,
relative to a human scale, yeah.
So immediately when you contemplate the size and scale of the universe, you ask questions about our place, and quite vividly, what does it mean to live these little finite, fragile lives? And so I think I try to approach those questions, and I realize that there are other lights you can shine on that problem, and science is a necessary, bright, and vivid light that casts a very well delineated shadow, which is giving us obviously it's the framework within which we operate. But there are other lights. So you realize that Mahler, for example, so we use Mahler in the classical concepts. Mahler thought a lot about what it means to live a finite, fragile life. And he gave a very eloquent answer, many eloquent answers in his symphonies. And he was once asked, by the way, what are you trying to say? What's this answer? And he said, well, if I could say it, I wouldn't have written the music. So,
good answer.
So you have this music.
I love that.
So the music, so the composers that I chose, and that they are in the tour that we're going to do this coming year, next April, 2025. They're in there as music. The composers were chosen because they explored this question and gave very eloquent answers. So it adds to, I think, the more philosophical exploration of the questions that are raised by the science.
What's the name of the tour?
Called Horizons.
Horizon. That's easy enough to remember. Okay,
Yeah.
very cool.
But there's a lot of black holes in it as well, I should say. And so it's an exploration of the ideas that I find
Black hole's
interesting.
a horizon of its own.
They have horizons,
Okay.
yes. But also life in the universe, the origin, evolution of life, speculations on, we could talk about it, speculations on how many civilizations there might be as a guess.
Well, this thing about life in the universe, you've done many TV series, and most recently one on the solar system.
Yeah.
Where the search for life is a main theme.
Well, yeah, we just saw, as we speak, last week, the Europa Clipper spacecraft was launched.
Yes.
On the way to Europa.
We have an entire show devoted just to that. We visited the Jet Propulsion Labs and
I saw
felt
that
the
being
excitement of everyone there.
It's great, isn't it? It's the first spacecraft I've seen, major spacecraft being built. So I saw the Clipper. And the thing is, the scale of that thing, it's the largest spacecraft, isn't it, that's ever been sent into the outer solar system.
if you add the
most massive. I think.
Here's it may be, but there's another important fact. Solar panels have gotten more efficient. In the day, back if you were going to explore beyond the asteroid belt, you couldn't use solar panels because the intensity of the sun wasn't high enough. This one has a very deployable large solar panel that'll help it along without having to rely entirely on the nuclear decay of plutonium.
Yeah. So it's a huge spacecraft.
Yes.
And the point is that Europa, Jupiter's moon, is a prime candidate for a habitable world. In the, what we know, almost certainly, I'm always, the people who I know who work on the mission say, don't say we know. We're almost sure there's a saltwater ocean below the surface. I think it's pretty indisputable now. So we're pretty sure it's there.
Yeah, but whatever is the skepticism, what would it be were it not a global ocean?
Yeah, it's very difficult to be because, and that's from many measurements.
Was it made of ammonia? I mean, there's not, water molecule is not rare.
Yeah. So it looks like salt water. Almost.
Yeah, and we have a lot of comparative planetology with, is it the Arctic, when it freezes over, you have these chunks of ice that will break and refreeze and readjust, and you can compare the images and you'd think you were looking at the frozen Arctic.
Yeah. So it looks, and there's more water in that ocean than all the oceans of the Earth combined, geologically active. There are questions about how the ice cracks and moves on the surface. So it's a fascinating mission. So that's Europa. Mars, of course, which you've probably spoken about many times on this podcast. Enceladus is another one, Saturn's moon. Even out to Pluto. I mean, even
Enceladus is the
Pluto.
ones we see the plumes of geysers, I guess.
Yeah.
When, at the right sun angle, you can see who took those pictures. That must have been Cassini. Right.
Yeah.
So,
and also there's some measurements from Cassini, the particles in those jets of water, which are consistent with hydrothermal vent activity on the floors. And hydrothermal vents are one of the plausible candidates for the origin of life on Earth.
yes.
So you seem to have everything. The one thing I think Europa's got that arguably nowhere else has is it looks like that ocean has been there for many billions of years. That's the baseline scenario.
And we evolved life in less time than that here on Earth.
Yeah.
Out of
I mean,
our
it was
oceans.
present, 3.8 billion years ago?
3.8-ish, yeah.
And the Earth's 4.5 billion years old. So,
Right.
Yeah, so it looks like you have a habitat that's been stable there. And I think that you can't claim that with anyone.
In fact, it was taught that it took about 500 million years on Earth to get life going. But we were able to revise that number down because in the early Earth, these periods of heavy bombardment, it's not fair to start the clock while we're still getting slammed by, still accreting leftover rocks from the solar system as the temperature of the surface of the Earth is high enough to prevent complex molecules. Give us a chance, please. So the periods of bombardment subside, Earth's surface cools, now start the clock. and then it's about 100 million years.
Yeah. So
And it's like that.
Which is one of the reasons I think if you speak to many biologists, they would say that might suggest that given the right conditions, then whatever the origin of life is, there's a reasonable probability given the right conditions because it happened quickly here.
Right.
So, but that's not definitive in any sense.
But it's certainly tempting to go there.
But what I find very interesting then is, though, when you ask, okay, but when did life get more complex than a single cell? You're then, I don't think there's any evidence in the fossil record back beyond about 600 million years ago.
It took a while.
Of anything.
Yeah, we languished as single-celled creatures.
3 billion years plus, but it seems.
So I think people who think about this problem are honest about that. And so in the search for life on other planets, we're really looking for single-celled organisms.
Well, it would be remarkable to see anything more complex. Well, it'd be remarkable to see a single cell, because then you'd know, especially if it were biologically different. So you can really show that it's got a different origin, because it's worth saying that on Mars, the material is exchanged between Earth and Mars. So it's not obvious that you couldn't.
And you make all these points in your series.
Yeah.
Right. So where can people find your series? It's streaming, I presume.
Yeah. We've got the new one is just on at the moment, actually.
That's what I'm saying.
So the solar system. So that will appear on Apple, I suppose, at some point, and other places. Yeah. Okay. I mean, at the moment, it's on the BBC. So and it's streaming on the BBC, and then it will head off around the world. One of the coolest things I think about Europa is that the habitat, the potential habitat, requires Jupiter, because the heating, it's liquid because of it's orbiting around a big planet. Mm-hmm. But it also seems to require the other moons, Io and Ganymede, to keep it in this orbital resonance, which keeps feeding the energy in from the gravitational field.
The family affair,
But it also might need the material from the volcanoes of Io on the surface of Europa, because they might provide what we call the oxidant, right? So life is. So
you're saying that an Io, which is badly stressed,
it's just one big volcano.
It's one big volcano. So it spews volcanic substance faster than escape velocity, apparently. And then which lands on Europa. And it goes into pathways that intersect other moons, Europa included. Yeah. And then, do this for 1 billion years.
And then the chemistry, and then it gets irradiated.
That helps out the chemistry.
Yeah. So one of the theories that I've spoken to people who are on the Clipper mission said is that that's part of the battery of life, that chemistry. So life, I can't remember who said it, but he said life. Someone said it's an electron looking for a place to land. That's what life is. So it's just, in one way, you can see life as electrons moving around. But that means you need the chemistry to is that all we are? Just electrons looking for a place to land? Well, that's what a description.
I'd rather be dust in the wind, whatever. All we are.
But I find that wonderful, because then you've got this habitat, which is a system. And as you said, comparative planetology you mentioned earlier, it's also true of Earth, isn't it? You can't understand Earth without understanding the system, the solar system. You need to understand the moon and how it stabilizes the spin axis, and you need to understand, of course, the sun and the way it interacts with Earth and so on.
I'm a few years your senior. I don't know if you would remember this, but I definitely do. The era where no one was thinking or caring about moons in the solar system. Yeah. We have a dead moon orbiting us, oddly large, but fine. Let's go look at the planets. Yeah. And so every mission out to the planets, they looked over their shoulder and found moons, which had way more geologic diversity than anything we're finding on the planet.
I found it interesting because
when you were in school, where were we?
Pre-Voyager. Voyager. So
see, I'm pre-Voyager, and Voyager turned the moons into worlds. Yeah, that's what happened. Yeah.
So the idea you have a habitable zone in a solar system, which is the zone within which, if you have a rocky planet orbiting and everything's right, and the atmosphere is right, you could have the conditions to support life on the surface. Well, liquid water on the surface, let's say.
Right.
And so. But
that turned out to be needlessly limiting.
Well, exactly. Yeah. So you just say, well, Mars, Earth, Venus in our solar system.
That's it.
But then you find habitable zones around gas giants. That, as you said, that was the great discovery of Voyager, I would say.
Yeah, it began with Voyager, really, for sure.
Yeah. It should be early 1980s, right?
So I'm delighted, even as a particle physicist, you get to also platform the solar system, Because you have the name recognition.
I was always, but that's why I said I started with astrophysics. I really just wanted to be an astronomer. So I've always been. I've got a telescope.
You confess to me.
No, I did.
It's a safe space to do that.
I ended up in particle physics. It was almost, so I was doing astrophysics. That's what I was doing. And I thought, I want to be an astronomer. University of Manchester has the Jodrell Bank radio telescope, for example, which is one of the big radio telescopes in the world still. And so
that wasn't the one that discovered the first pulsar, was it?
No, that was Cambridge.
That was Cambridge. Okay.
Yeah, Jocelyn Bell
Jodrell
Burnell
Bank discovered something else. I mean, Jodrell Bank.
It was one of the first, so it's one of the pioneering. It does a lot of the work on the Crab pulsar and so on. Okay. But it was so I thought I'd be an astronomer, and I have a telescope. That's what I do. I sit there and
you're
look
in the club. We'll accept you in the club, even though you drifted to particle physics
and space exploration. So that's but it was at university. I just got interested in mathematics. I didn't think I was very good at mathematics at school, and but I found out with a bit of practice, then I enjoyed it. So I ended up really getting more into theoretical physics and went that way. So that's why I ended up in particle physics, really. But then now, of course, I've every opportunity I get, I seem to drift back.
Because the universe is cool.
And black holes.
I want to brag about the universe, but...
And black holes, actually, are where they intersect. They absolutely, particle physics and general relativity, astronomy
and the Big Bang itself, of course.
Yeah.
With your particle physics hat, where are we with neutrinos now? I thought they're sort of fully understood. We solved the neutrino problem in the sun. A Nobel Prize was given for that. Is there anything left to discover about this elusive particle that belongs in the I would say tree of life, in the particle tree of life?
Yeah, I mean, there are neutrinos are fascinating things. They're very, 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 they're almost massless, but not quite.
And that matters.
That should ring bells. It's like, why? That's the thing about science, isn't it? You go, well, why is this unusually light? Or maybe it isn't. Maybe the other things are unusually heavy, but it's telling us something.
And it's only neutrinos, how hard it is to interact with them, that gives me any belief at all in some other set of particles that might exist that we don't interact with. Because neutrinos are our own species.
Well, they interact through the weak force. So they'll interact
but
through
that's us. That's our little world here, right? Yeah. Any other symmetric particles, there are other forces that mediate them. Is that correct?
There would be. So if you have sort of extensions to the standard model of particle physics, then you can have forces that change things into other things, and so different forces. But as far as we know, the zoo that we have discovered is described by the three forces: the strong nuclear force, the weak nuclear force, electromagnetism, and then hanging out there, as we've discussed, is gravity in really a different framework at the moment.
So I corralled Steve Weinberg in the elevator one day, and physicist. I'm telling the audience. Particle physicist.
One of the greats.
Yeah, and he went to my high school.
Did he?
Allow me to add one of
Nobel
our eight
Prize winner,
one of our eight
model.
Nobel laureates from my high school. And I said, how can you live with yourself at night, given how many particles there are? Come on, there's I lost count. What does this mean about our universe? And he said, it's not how many particles there are. It's how many laws we have that describe them all.
Yeah.
And it's only just a few.
Yeah.
I thought, damn, good answer.
Yeah. I remember Stephen Weinberg.
Good answer.
I think I'm right in quoting him as saying that he almost wished black holes didn't exist because they're so perplexing that it would be just easier. And he was kind of joking, of course, because physicists love a mystery. But he was almost like, this is too difficult. This too bizarre. Maybe nature doesn't make them.
Oh, I got it. So he's invoking human limitations on the capacity of nature.
Well, he was kind of joking. He was just saying these things are so baffling and so weird. Mm-hmm. In some ways, I'd rather they weren't there. You know?
Did he say that in his old age so that he was getting tired of solving the universe?
He was joking.
So we're still trying to explore neutrinos. And as I understand, there's a new neutrino experiment that just came online.
I mean, there are several. I mean, what the fundamental question, they do seem, the reason we're interested in them, we're interested in them because they're 3 of the 12 fundamental particles, right? So so we are made of basically 3 particles. That's us. And
the electron, protons, neutrons.
Well, no. So the protons and neutrons are made of quarks.
Oh, so okay.
So up quarks, down quarks.
Let's start from the Greek. We're made of atoms.
You can start with we're made of atoms, and what are atoms made of?
In Greek means indivisible.
Yeah.
That's what that word means.
Yeah, and it is remarkable, by the way. You say the Greeks 2,000 years ago, we only discovered the structure of atoms in the 20th century.
Or that atoms existed.
Well, yeah, it was up for debate. The turn of the 20th century, it was one of the debates in science. Is there such a thing as an atom?
Yeah.
It's incredible.
Incredible, yeah.
And Einstein, indeed, in 1905, one of his famous papers was on Brownian motion, which one of the 3 famous papers in that year. The other one was special relativity, and the other one, when he got the Nobel Prize for, was the photoelectric effect. So the third one. And it was
Einstein, we should just retroactively give him like a dozen Nobel Prizes.
It's astonishing.
Yeah,
he didn't get the Nobel Prize for relativity. He got it for basically the foundation to quantum mechanics.
Yeah.
We discover that matter's made of atoms. And then we very quickly discover after that the atom is electrons. Initially, we have this almost solar system-like model that it's a nucleus, a dense nucleus with an electron going around it. And then we discover the nucleus is made of protons and neutrons. That's 1930s, by the way.
That orbit model is still the symbol for an atom.
Yeah. The atomic
we kept it just because it's classic, but atoms look nothing like that.
No.
Right.
And so then quantum mechanics comes in, tells you can't have that because charged particles moving around in the vicinity of other charged particles radiate energy away and they wouldn't be stable. And that was known, of course. And so then you find that the nucleus is made of protons and neutrons. And as I said, the neutron, it's a 1930s discovery. So we're not that long ago.
I'm amazed when so much, we're now in the centennial decade of the discovery of quantum physics back in the 1920s. And the whole 1920s was done before we discovered the neutron. That's crazy.
Yeah. It's almost living, it is living memory for some people just about this.
Okay. So let's get back to the fundamental particles.
Yeah,
so
then we discovered that the protons and neutrons are made of quarks.
Quarks.
So they are, as far as we can tell, point-like objects. So they're fundamental. They won't be, but as far as we can tell, they are experimentally.
So we have the photon, the electron.
Well, let's take
quarks.
the matter particles. So the up and down quarks make up protons and neutrons. So a proton is 2 ups and a down, and a neutron is 2 downs and an up. Got
it. And we have 2 quarks per energy stratum here, correct?
Well, so then we discovered. So we have this nice thing. So we have the electron, as you said, the up and down quark, and then the thing called the electron neutrino, which we just talked about neutrinos.
So only 4 fundamental particles in anything we know or care about.
So we have 4 of them. Yep. That's it. And then we have
so I can construct you out of these particles.
Yes.
If I had the recipe.
Yes. But then, so we have 4 of them. So that's it. There's 4 of them, and then the forces that mediate the interactions, right?
Okay.
And which we can also think of as being carried by particles, as we said.
Okay.
We have the photon,
the massless particles,
the electromagnetic force. We have the W and Z bosons, which do the weak nuclear force, and the gluons, which do the strong nuclear force and stick the quarks together.
Aptly named gluon.
The gluons,
yes. Okay.
And so that's it. It seems, except that there are 2 copies of those that are identical, except they're more massive. So there's the charm and strange quarks, and the muon and the mu neutrino. That's another family.
That's the next level up in energy.
They're more massive.
More massive. Yeah. Okay.
So you have the charm and strange and the muon and the mu neutrino, and then
you have another one.
Yeah, which are the bottom and top, or sometimes called beauty and truth, depending on how you want to do it. The quarks, and then the tau and the tau neutrino. Okay. And that's it, as far as we can tell. So those are the matter
4,
particles.
8, 12 fundamental particles, and their antimatter counterparts.
Yeah, and then the antimatter counterparts. Okay. And so that why, we don't know. So why there are 3, and with experimentally proven, really, with some very small caveats, only 3 generations, only 3 families of these things.
Is there a reason for there to be only 3? Could there be 5 or 10?
So we don't know. It must be something to do with the underlying. So it looks like a periodic table. So remember, you go back to Mendeleev and the periodic table. how do you understand that pattern in the chemical properties of the elements? You understand it when you know that everything's made of atoms.
Yeah, I mean, the chemist arranged it, but didn't have any understanding of it.
No,
quantum physics.
Well, you need to know the structure. You need to know that there's a nucleus, and there's hydrogen's got 1 electron, and helium's got 2, and carbon's
alchemy only gets you so far.
Yeah. So you understand chemistry. You understand the pattern when you understand the building blocks.
Okay.
So we don't know why that pattern is there, but it's clearly telling us about the building blocks or the underlying theory, which we don't know. So it's one of the great mysteries. So that's the zoo of particles as we know. And then there's the Higgs.
And just to be clear, when I attacked Steven Weinberg in the elevator, most of the particle identities I was referencing are different combinations of different quarks.
So
come together.
Yeah, so all these, like you said, in the 50s, and people were discovering all these things, and they're different combinations of ups and downs and strange and charm and bottom and so on.
Mm-hmm. So they exist in our universe, but again, they're made of the more fundamental.
Yeah. So basically, these things, the proton and neutron, they're kind of analogous to an atom in a way. So they're a thing. They're quite big things in particle physics, and they have an internal structure. And one of the things that I was involved in that we did back in Hamburg all those years ago was we were mapping the structure of the proton. So we're saying what is in the proton? How does it work?
Mapping the interior structure of the proton.
And we need that. We needed that for the LHC. So we need, because we collide protons together. So we have very detailed maps, if you like. They're called structure functions, but they're maps of the proton.
Well, Brian, thank you.
Oh, pleasure.
For joining me.
I always love talking to you and being on this podcast.
We're kindred spirits in this world, and I wish you great success with your spring tour. Does it go beyond the United States? Is it a world tour?
It has been a world tour. We've been to, I don't know, 20 or 30 countries. As I said, we're probably approaching 500,000 people who've come to the tour.
So that's
we're at the end really of this one.
Oh, okay.
And so I just wanted to bring it back here. It's changed so much. We kind of started in the States actually with it in its proto form. And now I've loved doing it so much, and I just wanted to bring it back. I just
like the idea that a science talk is being given, but there are trucks that have to unload the staging for it.
It's proper rock and roll. I got roadies. I've got everything.
Do you have a tour T-shirt with the cities on it? Yeah.
Yeah. Oh, yeah.
All right.
I should have brought one to show you.
I want one of those shirts.
Yeah.
Oh my God.
Oh, we've got everything. And we've done so many shows. I don't know how many it is, 150, 200. They don't all fit on one T-shirt. So we've got different T-shirts for different regions of the world.
Physics takes the world. Very good, Brian. Again, thanks for being on the show. This has been an exclusive conversation between me and my good friend Brian Cox from the UK, who's coming stateside with a tour. And we're going to look for the solar system on Apple.
It should be around,
if it does its BBC. How many episodes is it?
5.
5 episodes. We'll look for it. All right. This has been Star Talk. I'm your host, Neil deGrasse Tyson. As always, keep looking up.